Hi everybody, how are you doing? Everybody's cool? Life is going on? Okay, so CNN, training, right? When we talk about training, we basically want to know how we can backpropagate over CNN. Once we know it, we can train it, right? That's just gradient descent. So today what we want to talk about is basically to get the idea how you can do backpropagation on CNN. And we do it this time a bit less detail as last time. And then for the next chapters, we're going to do it even less detail. So this one, again, we try a bit of backpropagation here to just see the fact that you can always write backpropagation is always very efficient to be done. Okay. Now, what we want to do, we basically want to find out a way to just update the learnable parameters inside a convolutional neural network, right? So there are a bunch of ways inside a CNN. So we have FNN. If you remember, when we design one complete deep convolutional neural network, we have a bunch of convolutional layers, right? And these convolutional layers are being at the end given into a feed-forward neural network, a fully connected one, MLP, right? And now, once you have done all of this, you are at the very end, and at the end, you do know, for example, what is the class of your image, right? Now, the thing that you want to do, this time you want to go back, right? And this means that you need to be able to backpropagate on every single of these modules, right? So on FNN, you already know how to do it, right? So every operation that you have, you just do pretty much the same thing, right? But using different weights. So these are the parameters inside your FNN. The next one that you need to just go backward over it is the convolutional one, right? And yeah, you also need to know how you can deal with the pooling, even though you don't have weights, and we're going to talk about that. Now, let's just write down the problem that we have. The problem is that we have a data set. We have a bunch of images, XB, right? These are, for instance, tensor RGB images, right? And they have class, right? This VB is probably one hot representation of the right class, right? And the thing that you want to do, you want to just find out the right weights. So this W contains all of the weights that you have inside your neural network. The way that we do it is, again, as before. So we're going to just send these X's over the neural network. We're going to see the output. Once we see the output, so say I send this XB over the convolutional neural network, you're going to go all the way towards the end. I'm going to get this theta, right? This is the output of the neural network for the particular sample B, right? Once I have this, I'm able to compute the loss between the output and the true label, right? I do it for a batch of data, a mini batch, say, of size B, and then I average over that, right? And what I want to do, I want to minimize it, correct? Everybody's cool? And the way that we do it is, what is it? Gradient descent, right? So I need to know the gradient. I'm going to use one of the gradient-based methods. Maybe I use SGD itself, or maybe I go ahead and use Atom, or I don't know, RMS prop, whatever, right? At the end, I need the gradient, right? And I want to update. This means that I need to be able to move backward and compute the gradient as well. So this is going to be the computation graph. Your image goes in. First convolutional layer gives you one computation. You activate it. You maybe do some pooling on it. You go for the next layer, right? Again, you do convolution, activation, bunch of other operations, right? Till you get to the very, very last convolutional layer. At that one, you are going to do flattening, right? Whatever you have computed, you're going to put it into one array, and then you pass it through one MLP, right? And once you have done that, you're going to get to your output. You're able to compute the loss, right? So forward pass goes over all of this network, going to give you the loss. And now the backward movement is what we want to do next, right? So first thing first, if I want to move backward from the loss up to the very last convolutional neural network, convolutional layer, I am able to do it easily, right? This is basically the backpropagation that we had before, correct? So up to this point, there is no problem at all, right? So everything is as before. The only new thing are these other layers, right? Okay, so I am going to compute that loss. I am going to backpropagate up to the beginning, the input of my MLP, the output MLP that I have inside my CNN, and I'm able to compute the gradient up to that point. That's quite easy, right? A bunch of backward passes like backward linear computation and activations. And at the end of the day, I am going to get this gradient with respect to the very input of the MLP, and I can resort it in the form of the convolutional output that I had. Everybody's cool? So for instance, say I had at the very end of my convolution, my last convolutional layer, I had a 2x2 map, okay? And I would say, okay, the first entry is the first one, second entry is the second one, like in the two-dimensional map. This is y1, y2, y3, y4, right? And I'm going to put it inside a vector of size 4. Now, when I do the backpropagation, I'm going to get a gradient of size 4, right? And then I'm going to resort it again in the form of a two-dimensional map, right? This is what I mean by this gradient of r hat with respect to yl. You see it here? So this is nothing but computing the backpropagation up to the beginning of MLP and then resorting in the form of the map that you had in your last output for the convolution. Everybody's cool? So up to this point, everything is okay. I can get that guy. Now the next thing that I want to do is to see how I can move backward on all of these operations that I have. If I want to do, if I have done any pulling, or if I have done any convolution. Okay? Okay, let's go ahead. Now, first thing, let's think about pulling. And I mean, it's obvious you need to always write down the chain rule, right? So let's think about pulling. Say I have the output, which is the output of the pulling. So if, for instance, I am doing a 2x2 filter pulling on this map here, so y1 to y9, this 3x3 map, is the one which is going inside, in the forward pass, is going inside your pulling. That green guy is the output of your pulling when you are doing forward pass, okay? Now, if you do that, say I have done the pulling, and among these first 4 in this patch, the largest one is y2, okay? This means that the output here is going to be exactly y2, right? So I go 1 next. Again, let's say that I look into these 4, and again, y2 is the largest one, okay? I'm going to write down y2 there, right? And so on. If I come here, for instance, say y7 is the largest one, so I'm going to put it here, and then I come here, and y9 is the largest one. I'm going to write down y9, right? Everybody's cool? So let's say this is what is happening inside the forward pass. Now, when you are moving backward, which gradient do you have? What is the gradient that you compute when you are moving backward first? Any idea? The pulling one, the green one, right? So you're going to have this gradient, the gradient with respect to y hat, the output of the pulling, right? And now you want to compute the gradient with respect to the input, right? The input of the pulling, because you want to go backward, move or propagate back the gradients. Everybody's cool? You see the problem? So you started from the very output of your CNN, which was the classified or the vector of, for example, probability, which was helping you classify your image. You were able to compute the gradient up to the output of your pulling, right? So you have the gradient of the loss with respect to the output of the pulling. Now, if you want to keep on going and be able to compute further gradients, you need to be able to compute the gradient of the input or your loss with respect to the input of the pulling, right? Everybody's cool? Questions? So I need to do that. What should I do? Chain rule, right? So I'm going to write chain rule. First of all, how does this gradient look like? It's going to be, again, the same map, right? But instead of having y2, y2, y7, y9, I'm going to have the gradient of r hat with respect to y2 here, right? Gradient of r hat with respect to y2 again here, and so on, right? Okay. Now, let's go back and use chain rule. First of all, I want to know what is the gradient of r hat with respect to y1. How can I write it down? Well, first look at this guy. How can I write it down? What is the gradient of r hat with respect to y1, the first entry in the blue map? What is it? It's going to be 0, right? Why? It's not included here, right? There is no entry there, so r hat is not depending on y1, right? So that gradient must be 0, right? And you can simply use chain rule. What you can say, okay, r hat with respect to any of those y hats, the output of the pooling, I have the gradient, right? The derivative of r hat with respect to any output of the pooling, I have it. I multiply that with the derivative of that output of the pooling with respect to y1, right? This is chain rule. If I do it for all values, all choices of I, then this is going to be the chain rule. Everybody's cool? Questions? And of course, none of those outputs depends on y1. This means that the second term here is always 0. Your gradient is 0, right? What about y2? Gradient of y2. What is it? Now, look at this one. You want to know what is the gradient of r hat with respect to y2, right? Yes?
It should be 1.
Sorry?
It should be 1.
What should be 1?
The gradient of r hat with respect to y.
R hat, not gradient of output, right? You're talking about the output, right? But even that one is not necessarily 1. With respect to two of them, it's 1. With respect to others, it's 0, right? Just look at this here. You have the gradient with respect to y hat 1 and y hat 2. You're right. Gradient of these two guys with respect to y2, both of them is 1, right? But the other two are 0, right? They do not depend. And you can again write down the chain rule, right? You could say gradient of r hat with respect to every single output of the pooling that I have times gradient of the output of the pooling with respect to y2, right? And then y hat I, when I is 1 or 2, both of them are y2, right? Everybody's cool? Do you want me to write it down on the board for you, or you see it on the slides? Now, what about, now if you got this idea, what is the gradient with respect to y3? 0, right? What about y4?
0.
y5?
0.
y6?
0.
y7? Exactly. The gradient with respect to y3 hat, right? Because y7 is essentially y3 hat, right? Everybody's cool? You see that? Okay. So this is going to be the case. So you can keep on writing down every single gradient using the chain rule. And then you have all the gradient with respect to input. Obviously, those who are not being pulled, they just simply get back with gradient 0 because they do not impact the loss anyways, right? And those which are getting pulled are going to somehow pass backward some gradients, right? Now, what you can think of it, now this is a bit less intuitive here, but we're going to see a more intuitive when we think about the mean pooling. But if you look at this one, now you can think of it in this form that, for instance, you start here with the gradient map to be completely 0, okay? So you have the complete 0 map, and you want to fill it out with the gradient of r hat with respect to y. How you can do it? Now, here in the index, you do know that when you were doing forward pass, you picked index 2, right? This means that this was the guy who was coming out, right, in the patch, correct? So you're going to keep this 1, everybody else 0, because everybody else does not depend, right? And then you're going to multiply this guy on this gradient that you got in your backward pass, right? You're going to multiply it. What comes out of it, out of this multiplication? Of course, everybody here is 0. Here you're going to have the gradient of r hat with respect to y hat 2, which sits here, right? Everybody's cool? Now, next, you're talking about this patch, right? In this patch, you would say that the index is 1. This means that when I was going forward, I actually selected this guy, right? I'm going to go and take this one, multiply it on this, right? And this means that only y hat 1 is going to come out, and anyone else is just masked, right? And you add it up on the map that you already had, right? If you keep on doing this, so next time you have index 3, so you're going to select this guy, this index here is 1, everybody else masked. So you're going to multiply this guy on this one, and you have y hat 3 just showing up exactly here, right? And the next one, okay? If you do this, then you're going to get exactly the gradient that I showed you in the chain rule, right? Now, looking at this kind of operation, what kind of operation you think it is? It's a sort of, reversed form of convolution itself, right? The difference here is that your filter, this guy, is changing each time with the index, right? And it might be a bit less intuitive to think about this, but it's going to get more intuitive if you think about mean pooling. Let's say that we have done mean pooling, okay? Let's say I have done mean pooling. What does it mean? It means that when I am going forward, I'll look at this map, yeah? I'll look at each patch, and I compute here y hat is the average of everybody inside the patch, right? Everybody's cool? Now, here in this case, every single guy here is actually passing forward some way, right? Because they are being included in the average, right? And then when that happens, this means that when you move backward, they're going to carry some gradients, right? Because they impact the loss. Everybody's cool? Okay, now, let's say that I have gone forward and then computed these 4 different values at the output of my pooling. And now the thing that I want to do, I have the gradient with respect to the green map. I want to compute the gradient with respect to the blue map, right? So maybe we can write down the chain rule once again. For instance, I want to know what is the gradient with respect to y1. What should I do? Gradient with respect to y1? Well, the intermediate computation here is y hat, right? So I can use chain rule. I would say the gradient of r hat with respect to y hat times gradient of y hat with respect to my input y, right? For instance, for y1, gradient of r hat with respect to every single of those y hats that I have at the output of the pooling times gradient of those outputs of the pooling with respect to the inputs of the pooling, right? Now, what is the gradient of y hat I with respect to y1? If maybe I write it down on the board. I guess like once I write it on the board, it's going to get easier. So derivative of r hat with respect to y1, you would say gradient of r hat with respect to y hat 1 times gradient of y hat 1 with respect to y1, right? Should I stop? No, because I had multiple y hats, right? And my r hat depends on all of them, so my complete chain rule needs to include everybody, right? So I'm going to write it down, gradient of r hat with respect to y hat 2 times gradient of y hat 2 with respect to y, with respect to y1, exactly. Because I am computing the gradient with respect to y1, right? And I keep on going like this, right? So I'm going to have the third term, which is y hat 3, right? And y hat 4, right? Everybody's cool? Now, if this is the case, now look at this one. Now, y hat 1, or y1, where does it show up? Does it impact y hat 1? Yes or no? Now, what is this gradient then? This derivative y hat 1 with respect to y1? It is 1/4, right? Because y1 gets added to y2, y4, y5, all of them divided by 4. This is mean pooling, right? So this means that y hat 1 equals y1 plus y2 plus y4 plus y5 divided by 4, right? If you take the partial derivative, this is going to be 1/4, right? What about this guy? What about y hat 2? If I go for y hat 2, does it include y1? Does it? No. So it's going to be 0, right? What about this one? Again, does not have the partial derivative. It's going to be 0. What about this one? Same, right? So this is why I have here only one term, right? Everybody's cool? Now, what about the next one? The derivative of r hat with respect to y2. Where does y2 show up? It shows up in y hat 1, right? Correct? It shows up in y hat 2, but it does not show up in y hat 3 and y hat 4, right? Everybody's cool? So if I write down the chain rule, then the term gradient of y hat I with respect to y2 going to show up by factor 1/4 in the first two choices of I, like y hat 1 and y hat 2, but it's not going to show up for y hat 3 and y hat 4, right? Everybody's cool? You see that? So it's going to be 1/4 gradient of r hat with respect to y1, 1/4 gradient of r hat with respect to y2, and that's it, right? Now, which term you think that is going to have, or which partial derivative you think that will have most number of terms? No.
y5.
y5, right. Because it is showing up in every computation, right? This is in the center. It is showing up everywhere, right? Everybody's cool? So when you keep on going like this, for example, each time you're going to get a bit of more computations, right? For y5, you have everybody, including y5, so everybody has the partial derivative 1/4, averaging them out, right? And so on. Again, you get back to y9. Everybody's clear? So you got the idea of the chain rule here? Now, you can think again the same way, right? You could say that I put all my partial derivatives here. I get this filter, which in the mean pool case is just 1/4 everywhere. Multiply it on that green map. I write it down exactly on the patch, right? And I keep on going forward. Each time, whatever I get, I'm going to add up with whatever exists on the map, right? So you can think of it, and I told you this is a sort of reverse form of convolution, right? But if you don't see it immediately here, we can actually see it in this case more visually. How can I do it? I could get this gradient map that I have. I can add 0 around it, right? I do 0 padding, and once I've done 0 padding, then I am able to get this filter. I convolve it with this one, and I end up by a 3×3 map here, right? If I do that, it's going to happen. And now I keep on doing the same operation. I keep on doing gradient. I get this guy, I put it here, I compute like this. These ways are going to get multiplied here, and obviously only this term is going to show up here, right? I just keep doing the convolution on this output map and write down everything on the other side. And if you go ahead and do the calculation, you're going to see that this is exactly the same calculation that we did in the chain rule. Everybody's cool? You see what's happening? So you actually do not need to do reverse convolution. You have your gradient map. You add zeros around it. You do 0 padding to just match the dimension, right? And then you get the filter. You convolve it on the gradient map in the output. You're going to get the gradient map in the input. Questions? No question? Everybody's cool? Okay. So that's it. When you are doing pooling, right? In the forward, you are doing, as we talked about, pooling is a form of simple convolution, right? And when you are going backward, you are again doing convolution. Before you get your filter, you convolve it with the input, right? Now you get the filter, you convolve it with the gradient of the output, right? And then you get the gradient of the input. That is the nice thing here, because you essentially do the same operation in your forward and backward pass, right? Convolution in the forward, convolution in the backward. Questions? Okay, so moral of the story, backpropagation when you are doing unpooling is essentially a convolution type operation, no complexity changed, and you can efficiently implement it. Now, the other thing about, the other layer that we have in the convolutional neural networks is the convolutional layer itself, which essentially consists of two parts, right? You first do your linear convolution, you compute the features, and then you activate it, right? And now you want to move backward. Activation, is it a big deal? No. I mean, you get your computation, you activate every entry, right? When you want to move backward, you multiply every gradient with derivative of the activation function, right? So it's not a big deal. The activation part is quite simple. You have your output, activated output, a function of your input. You can simply do this operation, right? You take the derivative of your activation function at every single point, and you multiply it to the gradients that you already have computed up to that point. This is the gradient of non-activated version, right? So gradient of z, or gradient of r hat with respect to z, is simply computed from the gradient of the activated version, right? That's not a big deal. The key point here is the linear convolution. And what do you expect to see again? You expect to see another convolution, right? So you probably expect to get a sort of filter getting convolved with your gradient at the output, and then you have the gradient in the input, right? And this is exactly what's going to happen. The only trick here is to know how to form that filter in general. Okay, let's do it together here. Let's say I have this guy, and it's x1, x2 till x9, and I have this filter which has 4 different weights. Every single weight goes and sits on the right patch, gets multiplied, computes one given feature at the output, right? So z1 is multiplication of these weights on this patch added up, and so on, right? z2 the same, z3 the same, z4 the same, right? And if I want to move backward, I have no other way but writing down the chain rule, right? So I do know what is the gradient with respect to z. This means that I started from very output, I just backpropagated over the MLP, then maybe there was a pooling, and then I backpropagated over that. There was an activation, I already backpropagated over that, right? I got the gradient exactly with respect to z, right? And now I want to get back from gradient with respect to z to gradient with respect to the input of the convolution, right? Everybody's cool? Questions? Great. So I want to get back from this gradient to this gradient, right? And how can I do it? Okay, I start writing down the chain rule. Let's just start writing down the chain rule for the gradient with respect to x1. And can you tell me what is the gradient of r hat with respect to x1? How can I write the chain rule here? It's going to be gradient of r hat with respect to, first, z1, right? Because I have the gradient with respect to all these entries at the output, right? And from that one, I want to get back to gradient with respect to x1, right? So I'm going to start writing down chain rule. I would say x is going through convolution, gives me z. Z gives me the loss at the end, right? I got the gradient with respect to z. Now to get back from z to x, it's going to be gradient with respect to z times gradient of z with respect to x, right? I just expand that term. So gradient of r hat with respect to z1 times derivative of z1 or gradient of z1 with respect to x1, right? Again, gradient of r hat with respect to z2 times gradient of z2 with respect to x1. And I keep on going like this, right? Everybody's cool? Questions? Now, look at this one. I want to know what is the gradient of r hat with respect to z1. I already have it, right? I don't need to think about it. Gradient of z1 with respect to x1. What is it? When I want to compute z1, how does x1 show up there? It's going to get multiplied to w1 and then added up to all other multiplications and then gives me z1, right? Then what is the derivative of z1 with respect to x1? What is it? Anyone can say it loud? Trust yourself. Be self-confident. What is it? W1, right? So it's going to be W1, right? Everybody's cool? Everybody sees that? Gradient of r hat with respect to z2, gradient of z2 with respect to x1. What is it? It's 0. Why? x1 is not showing up in the computation of z2, right? What about z3? 0. What about z4? Again, 0, right? So this guy is 0, the next guy is 0, the next guy is 0, right? And if you write down the chain rule, then you're going to have the same thing. W1 times gradient of r hat with respect to z1, right? Everybody's cool? Now, if we go for the next guy, what's going to happen? If I want to compute the gradient of r hat with respect to x2, well, I would have the gradient of r hat with respect to z1 times w2, which gets multiplied with x2, right? Again, I have gradient of r hat with respect to z2 times w1, which in the next computation is getting multiplied to x2, right? You see that? And of course, the other terms are 0 because x2 does not show up on those computations, right? So it's going to be like this, right? W2 gets multiplied to the gradient with respect to z1, w1 to the gradient with respect to z2, right? Everybody's cool? Questions? No question? Now, which term you think they're going to have most terms? Which partial derivative? Partial derivative with respect to? Go ahead. X5 again, all right? The guy in the center, which is showing up in every single computation, right? So if you keep on going like this, you're going to see that X5 going to have the most terms because it's showing up in every computation. The guys on the edge going to have a single term because they are only showing up in one term, like extreme edges. And the other guys are taking two terms, right? Because they are showing up in two computations, right? Okay. Now, if you want to visualize what is happening here, you can again do the same thing. You can say that I put the gradient at the output here. I get this guy. I multiply it to this one, right? And I write it down here, right? And then I go on next time. Again, I get this one, multiply it to that one. I write it down there. And whatever exists, I'm going to add it up there, right? And I keep on going like this. Again, this is not a very nice visualization. A better visualization would be this one. I could say that, well, I'm going to add zeros around this, right? And then I start convolving a filter with this guy to write down the gradients here. Now, what would be those terms here, those weights here? Just think about the very first term, right? This one, right? I am computing gradient of r hat with respect to x1. It means that this term is going to get a weight here multiplied with this gradient of r hat with respect to z1. What is that term? W1, right? So where should W1 sit on this filter? Where should it sit? Any idea? Where should be W1? Should it be on the top left corner? If I put it in the top left corner, obviously this is nowhere on the other filter, right? And then top left corner here gets multiplied by 0. You don't want that, right? Where do you want it to be? Bottom right, correct? So you want W1 to be here, bottom right, so that it gets multiplied to this guy. It shows up here, right? And you can go ahead and check the other terms, and you're going to see that if you just reform your filter in this form, like you do a flip top down, left, right, okay, you flip everything, then you're going to get a new filter, and when you keep convolving that filter with this new gradient, this gradient map at the output, you're going to get your gradient map in the input. Everybody's clear? Questions? So you got the idea? What's happening? So again, you're basically doing convolution as before. The only difference is that when you want to do the convolution, first you just reform your filter, right? It's just a resort of filter, right? Reallocation of the indices, which is a very easy task, right? A one-shot task you can do on your computer. Everybody's cool? Questions? No question? Okay. So, moral of the story here, if you want to backpropagate over a convolutional layer or a convolution operation, you basically do again a convolution of your flip filter with the output, and then you're going to get the gradient at the input, right? Exactly dual operation as your convolution. In the convolution, you get your filter itself, you convolve it with the input, you compute the output. In the backpropagation, you get the gradient up to the output, you get your filter, first you reverse it in the format that I told you, then you do the convolution, you get the gradient in the input, right? Everybody's cool? Questions? Okay, great. So that's the moral of the story, that the backpropagation is essentially, again, a convolution operation. So if Z is the convolution of X with filter W, then you essentially do the same operation on the output. So you get the gradient of the output, you convolve it with the reverse filter, this W reverse hat, this is what I want to show, this is the flip guy, right? You get left, right, up, down, flip one, right? This is what I call it here, I guess, yeah, reverse filter. This is just my naming, so it's not a very standard naming. I call it reverse filter, which is essentially the flip one, right? So you do the convolution with the flip one, then you get the convolution with respect to input. Everybody's cool? Questions? No question? Great. So if you got no question, then a few things here. The first question that might come to your mind is that, well, what's going to happen if I do this convolution in the backward pass and then the dimension does not match? Like if I do the convolution of the reverse filter with my output map, I do not exactly get the same size map in the input. Well, there are two reasons that you could get trouble. One of them is that you are doing your convolution with a stride. In that case, matching the dimension is quite tricky. Well, we're going to see that you don't really need this, right? As I told you, you always think about a stride 1 for now. And whenever you want to do a stride, real stride, you just simply need to do down or up sampling, right? And I'm going to explain you how you can backpropagate over a resampling module. and then that's it. Okay? So you don't really need to care about the stride right now. You can think about the stride 1 always, right? But the other thing is that, well, even in the example I showed you, the output was 2 by 2, right? And if you get the filter and you want to do the convolution with that output, this means that the gradient you compute is just one single entry, right? But obviously, you can do zero mapping to do that compensation, right? And you always do zero padding. No other trick. You just do zero padding around your map so that you get exactly this, the filter map that you want, right? Everybody's cool? Questions? No question? Okay. Now, I told you how you can compute the gradient with respect to input. And it makes sense when you are in the middle, right? Because you computed the gradient with respect to output. Now you need to know the gradient with respect to input because you want to pass it further backward to the other layers, right? But somewhere in between, you want to know what is the gradient with respect to the weights of the filter, because at the end of the day, these are the guys which you are going to update, right? Everybody's cool? Yeah? Now, how can I do that? Well, what do you expect to see first? Again, convolution, right? You expect to see convolution, makes sense, right? Convolution is a linear operation. Partial derivative should be again linear. And then all of the operations should show up again as a same linear operation with maybe a deformed form of filter, right? So you're going to see it again, right? Now, let's do it together. Say that I have x, I have z, I do the forward computation, I get the gradient with respect to z, right? It was when I was moving backward. I got the gradient with respect to my computation in the convolutional layer. Then I do know the input x. Where did I get x? When did I compute x? When I was moving forward, right? I computed x to compute z, to compute y, and so on, right? So I have all of these guys in between, right? So I computed x, I computed the gradient, and I got to the output of the convolution, right? I have these two. I want to know what is the gradient with respect to the filter, right? Everybody's cool? So how can I do that? Well, I start writing down the gradient of r hat with respect to first weight. What it would be? Well, you have the gradient with respect to z, right? What should you do? You should get that gradient, multiply it to gradient of z with respect to weights, right? Exactly, right? Now, you're talking about weight 1, then you're going to write it down in this form. You would say gradient with respect to all outputs times the gradient of every single of them with respect to W1, right? Everybody's cool? Questions? Now, can you tell me what is the gradient of Z1 with respect to W1? What is it? That is x1, right? Because W1 gets multiplied with x1, W to x2, W3, x4, W4, x5, added up, right? When you think about the gradient with respect to W1, it's going to be x1. What about the gradient with gradient of Z2 with respect to W1? What is it? It's x2, right? Everybody's cool? You see that? What about this guy? x4. What about this guy? x5, right? So you can write it down for every single way that you have. So you could say here that gradient with respect to gradient of Z1 with respect to W1 is x1. Gradient of Z2 with respect to W1 is x2. Z3 with respect to W1 is x4. Z4 with respect to W1 is x5, right? And you can keep writing down everybody else in this form, right? Everybody's cool? Questions? No question? Okay. Great. Now, if you think about this term that I showed you, like if you just do a bit of math, then you're going to see that essentially this first gradient that you computed is nothing but the first term when you convolve your gradient as the filter with your input. If you get your gradient, exactly the same gradient you had at the output, you put it here as the filter, you convolve it with the input, then the first term is going to be gradient with respect to W1. The second term is going to be gradient with respect to W2 and so on, right? So, moral of the story, if you are moving backward and anywhere in the middle you want to know what is the gradient with respect to the weights, what should you do? You get the gradient at the output, you treat it as your filter, you convolve it with your input, right? This is going to give you the gradient with respect to your weights, right? So this is again the reason that we do not care about the gradient with respect to the weights when we are developing the backpropagation. Because we say if we have all gradient with respect to outputs, we effectively have all the gradient with respect to weights. This is the same thing that we did in MLP, right? In MLP, when you are moving backward, whenever you want to compute the gradient with respect to any layer, right, you get the output gradient, you inner product it with the input, right? And that gives you the gradient with respect to weights. Same thing is happening here. Everybody's cool? You find it interesting or not? Is it like, oh, yeah. I mean, first time I saw it, it was like, oh, yeah, interesting. Okay, cool. So, moral of the story, when you are computing the gradient with respect to the filter, if you want to compute the gradient with respect to the filter of the convolutional layer, you basically do again another convolution. So you could say if Z is the convolution of X with W, then the gradient with respect to weights is convolution of X with the gradient of Z, right? And that's, again, a gradient convolution operation. You can effectively implement it, right? As long as you have one function on your computer getting two maps, computing the convolution for you, you can use it for forward and backward pass, right? Any questions? No question? Cool. So if you got no question, then let me go ahead with a bit of more complication. That is the case of multi-channel. So if I have a multi-channel convolution, this means that, multi-channel input, this means that my filter must be multi-channel as well, right? So I have a C-channel input, then my filter is going to be again C-channel filter, right? Every time the filter is going to sit on the patch on the input, I do all the multiplication, add up everything, it's just one feature, or write it down in the corresponding entry in the output map, right? Everybody remembers that, right? You recall it? Okay, now, for now, let's think about this case that I have X, which has C channels, and then I do convolution with one single filter. This is why I have just one single output feature, right? Once you understand that, the next one, like the multi-channel to multi-channel, is not a complicated thing. Okay? So I have one filter. My filter has the same number of channels, and then I can write down my convolution in this form. Okay? And this is the whole trick that you need to realize if you want to do the backpropagation in this case. Everybody, please take a moment, look at this equation, and tell me if you see that is correct or not. Do you think this is correct or not? Let's say I have two input maps. This is one map, okay? This is the second map. So this is X. x1, the first map inside my tensor, this guy is x2, right? Is it colored? No. Don't have. No. Okay. Now, how many channels should my filter have? 2 again, right? So this is my filter. It has 2 channels, right? I'm going to show it by W1 and here W2, right? Everybody's cool? Now, the way that I told you for doing the convolution, you're going to get these 2 maps. You put it on the first patch, right? So it means here and here, right? This guy, W1, is going to sit here. W2 is going to sit here, right? You multiply everything, you add them up, right? And you write it. Then you're going to shift everything one step further, and you do the same thing and so on, right? Now, let's say that I get this filter W1, right? This channel of the filter W1, and I just convolve it here on the first map. What's going to happen? I'm going to get this guy, put it here, do the multiplication, add up, but I do not add it up here, right? I'm going to get one term which is the one map like this, which is the convolution of x1 with w1, right? Correct? And I do the same thing with this guy, right? So I can get another map here, which is convolution of x2 with w2, right? Now, what is my true map Z in terms of these 2 maps? Addition of them, right? Because when I wanted to compute this first entry here, I got this guy, right? I got this guy, did the multiplication and add them up, right? Correct? Now, if I don't add up them immediately, so it means that I'm going to add up things here, and I write it down here, right? I add up things here, and I write them down here, right? How does this guy depend on these 2 guys? It's the addition of these 2 ones. Everybody sees that? Yes? Everybody's cool? Questions? So you can essentially write down your convolution with a tensor in this form, right? You would say every single channel of your filter is getting convolved with every single channel of your input. And once you have the output channels, you add them up and you write it down as a feature map. Everybody's clear? Okay, so if I write it down in this form, then it is not a very complicated thing to write down the chain rule. Because I would say, okay, the first map gets convolved with this filter, second map with its own channel in the filter, and so on, till the last channel getting convolved with the corresponding channel in the filter, right? And then I add everything up. This is how I build my output filter, right? And now, what I do have the gradient of r hat with respect to z. I want to know what is the gradient of r hat with respect to x, right? Everybody's cool? So, let me do it here for you. First, I have z equals to summation c from 1 to capital C convolution of xc with wc, right? Now I do have the gradient of r hat with respect to z. I want to compute the gradient of r hat with respect to one of the channels, say x1, the first channel. How can I write it down in terms of that gradient? I can use chain rule, right? I could say that this is gradient of r hat with respect to z times gradient of r hat, gradient of z with respect to x1. Correct? Everybody's cool? Questions? Now, if I call this guy here that I have computed, if I call this guy to be ZC, I could have written this that this is gradient of z with respect to z1, for instance, times gradient of z1 with respect to x1 plus z2 x1, z3 x1, and so on, right? So I can write it down as summation c from 1 to c. Here I have zc, and then here I have zc as well. Everybody's cool? But these terms that I'm writing down, what is the gradient of z1 with respect to x1? Does it exist? Is it non-zero? Look at z1 here. z1 depends on x1, right? So it should be non-zero. What about z2? Look at z2. Does it exist? No. I mean, z2 depends only on x2 and w2, right? It does not depend on x1, right? This means that that guy is going to be 0. The next one is going to be 0, and so on, right? So essentially, anyone else here is 0. I just need z1 here, and I don't need this summation at all, right? And now, gradient of z with respect to z1, that is simply 1, right? Because z itself is z1 plus z2 plus z3, and gradient of z with respect to any of those is simply 1. So this guy is also 1, right? So what you end up with is that your gradient with respect to the first channel is gradient with respect to z times gradient of that z1 with respect to x1, which looks exactly the same thing as we did in the two-dimensional case, right? So this means that when you think about one channel here, since everybody else is just adding up here, as you go backward, you don't care about them, right? And your partial derivative with respect to this guy is going to simply be another backward convolution. Now, you might find it a bit like compact, the way that I explained it. I don't want to bother you further with just giving all the details. But if you want, you can go home, again, open up this whole term that I wrote on the board. Just do the chain rule. You're going to see that it's going to happen. So moral of the story here is that if you want to move backward, the thing that you are going to do is to do just partial convolutions with respect to every single channel of your filter, right? So what does it mean? It means that you had your x, which was C channel, and now you have your output gradient, which is a single channel. You get this output, you convolve it with the reverse filter of channel 1. This is going to give you the gradient with respect to channel 1. You again get channel 2, you reverse it, you convolve it with the same output, you're going to get your gradient with respect to channel 2, and so on. Okay? Everybody's cool? Questions? No question? So now, one trick that I told you before was to always check the dimension, right? And again, this is going to be valid here because you have your input, it's C channel. Your output is a single channel, right? And then you have a C channel filter. You do know that getting from the output gradient to the input gradient, you need to do another convolution. You also do know that I need to do a reversion here, right? So it means that every channel in my filter, I'm going to do top, left, right flip, right? Once I have this, now I want to use this stack of filters to build a C-channel gradient, right? The only way that you can do is that you get every single of these channels and you convolve it with the output, right? This is going to give you a C-channel gradient at the input. Everybody sees that? So always if you play with the dimension and you do know what is the kind of operation you need to do in the backward, you probably can guess it without even doing the convolution. I mean, I do know at the end of the day it's PyTorch who does it, right? But it's important that you know what is happening, right? Questions? No question? Okay, so moral of the story, you can compute your gradient with respect to the input using, again, convolution, but now you need to stack it in multiple channels to build a kind of multi-channel gradient map at the input, right? Okay, now let's get to the last part. The last part is that if you really want to do multi-channel, okay, this is basically what this is just the visualization of what I explained. So you have your gradient with respect to output. You're going to convolve it with the reverse form of the first channel. You're going to get your gradient with respect to the first channel of the input, and so on till the last channel, right? Okay, now, last thing, let's say that I have one input, which is C channel, and then I have k different filters. This means that I'm computing a k channel output, right? Every channel at the output is computed by one of those filters, right? So C channel input, K channel output. This is your general form of convolution, right? Now we want to understand how we can backpropagate. First of all, what do you expect to see as the operation that you do? It's again a convolution, right? Since you have multi-channel output, multi-channel input, then it should be a kind of multi-channel convolution. It means that you need to have multiple filters, right? Getting convolved with the multi-channel gradient at the output gives you multi-channel gradient in the input, right? Now, let's think about the dimension, and probably it's going to clarify what we need to do. So I have the input, which is so I have this input, which is C channels, right? So I assume that I have C different channels here, right? X1, X2 to Xc, right? And then each of them is getting convolved with one filter, right? So I have, for example, W1. This is W1, filter 1, right? And so on till WK, right? This guy gets convolved with this one. And then it's going to give me the first map, Z1, right? Till the last map, ZK, right? Everybody's cool? So this is your output, right? You do have, so your output again looks like a tensor. It's a tensor, right? But the depth of this tensor is now k, right? It's not c. If I have the gradient of r hat with respect to z, how does it look like? What kind of object is the gradient of r hat with respect to z? It's a k-channel tensor, exactly. So it's going to look like this one, right? Everybody's cool? Now, what about the gradient of r hat with respect to x. What is it? It's a C-channel tensor again. So it's going to look like this guy, right? Now, when you are going forward, you have C-channel filters. You do the convolution, you get k different channels. Now you want to get back from this guy, which is k-channel, into a C-channel input, right? How can you do it using a convolution? How many filters do you need to convolve with z, with this, gradient? C different channels, right? You need C different channels because after convolution you want to get C different maps of gradient. What should be the depth of every single filter? It should be k, right? Because your output is a k-channel tensor, right? Everybody's cool? Now in general you need to have C times k different filter channels, right? Correct? Do you have that much channels? What is the depth of every single filter here? It's C, right? Correct? So you have k different filters. Each of them is C channel, right? So in total, you have C times k different channels, right? You just need to resort them, right? Group them into the form of C different filters, each of them being k channel. And then you're going to have the one you want. Any idea how I can group them? Let's look at this one. This is W1, and this has its own first filter, channel W1, channel 1, so on till W1, channel C, right? And then you have WK, channel 1 to WK, channel C. Now, I want to make, first of all, obviously I need to just reverse all of them because I do know when I'm moving backward everything is going to get reversed, right? So just a flip. Now, after that, how can I group them into C groups of k channels? First one here, first one second, first one last filter, right? Correct? So if I do such grouping, so it means that, it means that I get this first channel here, right? And go in the second filter, take its first channel again, till the last filter, first channel, right? I can group them into one new filter, right? So it's going to be W1 reverse channel 1, right? W2 reverse channel 1 again. WK reverse channel 1, right? Now, if I do that, how many channels do I have? K different channels, right? And how many of these groups I can make? C different, right? I go for the first channel here, one group. Second channel here, second group. And so on till the last group, right? Everybody's cool? So if you get this output, you convolve it with these C different filters, you're going to end up with this object, right? And that's correct. That's exactly the term that you're going to get. Everybody's clear? You get the idea? Questions? No question? Do you see that, or you just want to get rid of me? Like, yeah, that's fine. Go ahead. Okay, so yeah, you can go ahead and do a bit of like derivation as well if you wish, and you're going to see it immediately. Well, every single channel at the output is one tensor-like convolution. So you would say that X is of this multi-channel format, and this is going to get convolved with k different filters and gives you k different channels at the output. And then you can just think about a very generic form of chain rule, right? So you can use this notation. This is something that I initially told you, like intuitively you can always do it. Here I am just defining it a bit more formally. So you can misuse this notation of gradient of A with respect to B when you think about any general two objects. So A is one object. It could be any form of array, and B is any form of array with as much channels as you want, right? It could be even 4, 5, 6-dimensional tensors, right? Array of a tensor, array of tensor, right? And so on, right? You can think about this. Obviously, you have simple formats in mind, like if A is a scalar, B is a scalar, so you can think of it as a zero-dimensional tensor, zero-dimensional array, then this is simply a derivative, right? Gradient of a scalar with respect to a scalar is derivative, right? Gradient of a scalar with respect to a vector is going to be that thing that you usually call it gradient, right? If you talk about A and B, both of them being vectors, then it's Jacobian, and you can keep on going higher dimensions, right? But in general, you can always use this notation, and you can always call it gradient. That's okay, yeah? First order derivative of a bunch of scalars, bunch of parameters with respect to a bunch of other parameters, right? You can always do that, right? And if you do it, then you can always write down the chain rule with that notation, right? The only difference that is here is that those products that you do typically in basic chain rule, you just multiply things together. You need to figure out what kind of product you need there, right? And well, it's not hard. I mean, when you keep on working with arrays, it's not hard for you to see immediately what is that kind of product, right? If you, for instance, have two vectors and you want to end up with a scalar, obviously it's inner product, for instance, right? Two vectors, you want to end up with a matrix, out product, right? And things like this. But you can generally misuse this notation. Yes?
Here it can also mean convolution.
Sorry?
Here it can also mean convolution.
That product?
Yeah.
Yes. The operation of product is convolution, yeah. So actually, convolution is a form of product, right? You're right.
So this general notation that we're introducing encapsulates all types of
All types of operations, right, right. That linear operations that take two objects and give you another object, right? You can write it down in this form. And if you do this, then you can now write down chain rule. So you could say, if, for instance, I have r hat, which is coming from one tensor z, and then that tensor z itself is coming from another tensor x, then gradient of r hat with respect to x is gradient of r hat with respect to z times, and this multiplication you need to figure out what it is, gradient of z with respect to x, right? And again, I'm misusing this notation to just show any first order derivative. Now, if you think about this, then what you can say that I have gradient of z with respect, or gradient of, sorry, r hat with respect to z, the output of the convolution. And the thing that I want to do is to find out the gradient of r hat with respect to x. Well, this means that I have the gradient with respect to all maps at the output. And I can start writing down things in this form. So I could say the first map, right? The first output map is the convolution of x with first filter, right? And I'm going to call it F1, right? Just to abbreviate all the notation, right? To just shorten all the notation, I'm going to call that convolution of the first filter with the input to be F1, right? And so on till Fk. So every single of them is a separate function. And if I want to write down the chain rule, I could say that the gradient of r hat with respect to x is essentially gradient of r hat with respect to z1 times gradient of z1 with respect to x, right? Gradient of r hat with respect to z2 times gradient of z2 with respect to x, and so on, right? Everybody's cool? Now, do you remember this operation? If you have one single map at the output, just one single map at the output, and you have x as the input, what is the backward pass? It's again the convolution, right? The only difference in the convolution is that the filter is reversed, right? You remember that? So this guy is essentially what we computed before, right? If you have a single map output, then the gradient is that you get your filter, you flip it, and then you do the convolution again, right? Correct? So every single map is coming from one separate filter, right? And if you think about just one of them, right, that one is the previous operation we talked about, right? So you can write it down in this form, and you would say, okay, this guy is essentially the gradient of r hat with respect to that particular map multiplied with the corresponding channel, right? So this guy you see in the brackets, this tensor, is this one gradient for one particular k, right? And if you are doing chain rule, then you are going to add up everybody, right? Everybody's cool, yes? So you essentially do that operation that we did before for every single map, and then you sum them up, right? That makes sense, right? That's going to get you from one map into C channel input. You have k different of them. You add up them, right? But then you can again play a bit with this guy. You can take this sum inside the bracket, right? So you wouldn't say that I have tensors and I add them up. You would simply say that I add up corresponding channels, right? So this means that I can get this guy and write it down in this form, right? Everybody's cool? And then every single of these guys that I told you is essentially, that you see here, is essentially what I told you before. Because if you look at this one, you get your map, you get your channel 1 from filter 1, you do the convolution, plus channel 1 of filter 2, you do the convolution, and so on, right? So this guy itself is again a convolution, and in this convolution you have Z1, and your filter is actually that filter that we sorted on the board, okay? Now, you can go ahead and look, if you look at this one, you can define this sort of filter. So you can say that if I focus on one particular channel at the input, then essentially I get my corresponding channels at the all the channels at the output. The corresponding channel in the filter, I convolve every pair and then I add them up. And this is essentially again a tensor-like convolution, right? Everybody's cool? So I do see that some faces would tell me this too fast explaining it, but I don't want to spend too much time on something that it's just a simple calculation. You can again do it at home. If you got what I did on the board, that was the important part. Then you got the main idea. Okay? So you can go ahead and define this form of reverse filter. So this particular filter is this guy, right? So this reverse filter is containing channel 1 of every single filter, right? And this is for a general channel C, right? So if you think about channel C, you go ahead and collect channel C of every single filter, right? Then this guy is going to be, what is the number of channels in this new filter? It is K, right? So 1, 2 to K, right? So K different channels at the output. You have a K channel at the output, you can build a K channel filter, and then essentially what you're doing is that you get your output gradient and you convolve it with this particular filter, right? So it's again a three-dimensional, tensor-like convolution, multi-channel convolution, but the filters are the resorted. Everybody's cool? Questions? No question? Okay. So I'm sorry that I have been a bit over time before the break. I just wanted to finish this one up because I didn't want to just lose the lead, because then it's going to be hard to explain it from scratch. So moral of the story, if you backpropagate in a tensor-like or multi-channel convolution, then essentially what you do in your forward pass, you do a multi-channel convolution. In the backward pass, again, you do multi-channel convolution, same as before. The only thing that you need to do is to just resort the filter, right? Just flip every single channel in all the filters that you have. You resort them, you regroup them into the right format, and then that's it, right? And this is the main reason that people found it extremely efficient. Nowadays, it might sound quite trivial, but old days, like in 1998, when LeNet was implemented, it was really helpful to have such operation, right? Because your forward and backward operation was exactly the same format. It was easy to implement and efficient to follow up all the gradients. So, questions? So that's essentially what I explained, right? So you reformat or resort your filters, you do again a convolution. Now you have the convolution with respect to input, right? And what if I want to compute the convolution with respect to gradient? Convolution with respect to gradient. I want to compute the gradient with respect to filters. It's going to be again a convolution, right? You look at multi-channel outputs that you have, you look at the multi-channel input that you have, you convolve them, you're going to get all the convolutions that you want on the filters, right? You have K-channel output, you have C-channel inputs, right? You can do the convolution in a way, if you get every single gradient map in the output and convolve it with the corresponding map in the input, you're going to get one map, right? And that map is the convolution of the corresponding filter. So I'm not going to complicate things anymore to just explain that, but I hope that you get this idea. Convolution is essentially a linear operation. When you do backpropagation, you always do a gain convolution. The only thing is that you need to resort things properly. Right? Questions? Backward with convolution, you have a gain convolution. You need to resort your channels properly to be able to do that. So for an activation, you essentially do exactly the same thing as we did before. So it's an entry-wise operation again, and after that you do a multi-channel convolution to compute the backward pass. And yeah, this is basically what I explained there. So you can resort your filters in a way to build the filter that you want to be able to just do the convolution with the output, right? Now, everything that we talked up to this point works fine. So we have the pooling, we have the convolution backward, everything is over. The only thing left is what's going to happen if we have a stride not equal by 1. Because all the stories I told you here works fine with the stride 1. What's going to happen with the stride different from 1? Well, you could think of the case where you have a stride non-equal to 1, and then you would say, oh, the backward looks like a convolution with inverse stride. You can think of it like this. But the easier way is the one that I told you, that you think about that stride always as a resampling operation. So when we are doing convolution with the stride more than 1, we are essentially doing the convolution and then we downsample, right? This is what we talked about before. So convolution with the stride 2 is equivalent to doing a convolution with the stride 1, and then you do downsample with factor 2, right? Now the question is that if I have done this, so if I have done already the convolution with the stride more than 1, and I'm going backward, how can I go backward on this downsampling operation, right? How can I do it? Well, we're going to write down the chain rule, obviously. So I have x1, x2, x3, and so on till x9. If I downsample it by factor 2, what's going to happen? What's going to be the map at the output? I'm going to get rid of the second row column here, second row here, right? So the things that are left, z1 is x1, right? What about z2? What is z2? It's going to be x3, right? z3 is x7, right? And z4 is simply x9, right? Everybody's cool? Now, you can go ahead and do the backpropagation again. Chain rule again. So I could say gradient with respect to x1. Well, x1 is definitely showing up at the output, right? And if you do have the gradient of r hat with respect to z1, that is exactly the gradient of r hat with respect to x1. Yes?
Just like max pooling, but the index is always 1, right?
Sorry?
Like max pooling, but the index is always 1 in a weird way.
Somehow, yes, yes. Yeah, you can call it, but we're going to have a better representation. So gradient with respect to x1 is essentially the gradient with respect to z1. What about the gradient with respect to x2? Get back here. x2. It's going to be 0. Again, you could say x2 does not show up in z at all, right? And so it is not computing the loss, so there is no reason for it to have a gradient. And if you again write down the chain rule, you're going to see the same thing, right? Because every single z that you have is something different from x2, right? And then it's simply 0, right? So you can keep on going like this, right? For x3, it's going to be the one you have for z2 and so on, right? So this is what you're going to see. If you have this gradient at the output, how do you put it here? The gradient with respect to x1 is this guy. The one in between is 0. The next one is gradient with respect to z2. What about the second row? None of them show up in the output, right? All of them have gradient 0, right? And same thing for the last row, right? So it's going to be this format. So what are you doing in the backward pass? Upsampling, right? So you did downsampling with factor 2. You now do upsampling with factor 2, right? So it is upsampling with the same factor, right? So you don't really need to think about this stride, right? Just go on with the stride 1. Whenever you want to change the stride, do downsampling and keep on going. When you are doing backpropagation, the moment you get into downsampling, first you upsample, and then you keep on doing whatever you are doing, right? Everybody's cool? Yes? Sorry? Computational, yeah.
Like, does PyTorch perform the entire one thread?
No, it does it this way. And the reason is that you have GPU, right? And they are perfect in doing those simple tasks, multiplication, addition.
So we're fine with wasting a few multiplications?
A bit of, yes. We're wasting a bit of that, but it comes at the benefit of having, you know, a more efficient implementation, right? Right. When you want to instruct you. But definitely you can reduce the computation in that sense. Probably at some point of time people were doing it. I mean, anyways, if you remember what we did in the VGG 16, we essentially do not use a stride at all, right? So whenever we want to do that, we just do pulling, right? But yes, the typical implementation is this one, because that is more efficient in terms of coding. And one thing else, if you do it the way like very efficient, then you're going to get into a bit of complexity in terms of memory allocation, right? And this might somehow make all of the saving you have done redundant. So this is also one of the reasons. So now let's think about upsampling. So if I do upsampling, I get this x1, x2, x3, and x4. And I'm going to put them in the corners, right? I'm going to have these x's on the corners. Anything in between is going to be 0. This is one I do upsampling with factor 2. And you expect that the backward pass would be downsampling, right? And if you expect that, you're totally right. So here you have a reverse operation. Obviously, you want to get from this guy into this one. It's resampling, so you need to do, again, a resampling. But you need to choose your resampling a way that the dimension matches. This is basically downsampling with factor 2. And it's not hard to see it. For instance, you would say, what if I want to know the gradient with respect to x1? Well, x1 here is only showing at z1, right? And anyone else is simply not depending on x1, right? So here, this is going to be gradient on with respect to z1, right? What about gradient with respect to x2? again, you would say, if I look at this map, x2 is only showing at z3, so this is going to be the same gradient, right? Anyone else is 0, so it's again going to show up like this, and so on, right? So for 4 different inputs, x1 to x4 that you have, you can simply use chain rule to write down the gradient. They are going to be the gradient of the corresponding z's, right? And anyone else, you don't care about them, right? They are going to get downsampled anyway. In upsampling, they are going to set 0 anyways, right? So this is how you can think of. So if you have really these gradients here, this 3 by 3 gradient, and this was computed from the 2 by 2 map by upsampling, then when you go backward, you're just basically doing downsampling, right? Everybody's cool? Questions? Now I have one tricky question. These guys in between here, right? These are the ones which you added by upsampling, right? Look at this guy here, right? So you put these zeros with respect to by upsampling, right? When you are going backward, what do you think about these gradients in between? Are they 0? Think about it. Don't answer quickly. Are they 0? No, not necessarily, right? Do you know what is the reason? If I put one input to be 0 in a function, right? And I go forward. When I move backward, do I necessarily get 0? Is the derivative of the function at 0 necessarily 0? No, right? So it might be that these values are very well non-zero values, right? But you don't care, right? Because when you are moving backward, you're going to get rid of them. You downsample, right? You forget about them. Everybody sees that? Yeah? So if I have one function, right, and I force the input to be 0, then the output is that function at point 0, right? And then when I compute the derivative is simply the derivative of the function at point 0, right? Which there is no reason for that derivative to be 0, right? Think about function f equals by x squared plus 3. And so now it's not a good, it was the worst idea. X squared plus 3x, right? So your function is x squared plus 3x, right? If I force the input to be 0, the function is 0, right? But it doesn't mean that the derivative of the function at point 0 is 0, right? The derivative is 2x plus 3, which at point 0 is 3, right? So these values in between, there is no reason for them to be 0, but you don't care. You're going to downsample, right? It's the same thing like the dummy input you add when you want to add the bias, right? For that one, you put 1, right? And when you are computing the gradient backward, you simply drop it, right? Because it's not connected to the previous layer. You don't need to carry any gradient, right? Even though the gradient might be non-zero, right? You don't care. Here is the same thing. Okay, so here you have the downsampling, and the whole moral of the story here is that when you are doing resampling, the backpropagation is again resampling. Upsampling going to be downsampling. Downsampling is going to be upsampling. Same factor, right? Everybody's cool? Questions? Now, that's it. Pretty much anything that you need to know if you want to really train or implement the training loop of a CNN from scratch are these particular operations. So if you have, in forward pass, if you have a forward MLP, right, the backward is as before, right, the backward MLP. You get to the output of the last convolutional layer or pooling layer, whatever that is, If it is a pulling, then again going backward is a reverse form of that, right? Is a simple reverse convolution, right? If you have a convolution, the backward is again convolution. Simply you reverse the filters, right? If you are doing upsampling, the backward is simply downsampling. If you are doing downsampling, the backward is simply upsampling. So every operation you're doing forward, you do the complement in the backward, right? And this is why CNNs are very efficient, very lovely, right? You can simply implement it, right? You basically need to write down one function, one general function convolution, in addition to the linear operation and activation, in order to be able to train these guys, right? Everybody's cool? Questions? No question? Okay. So that's it. Well, once you have all the gradients that you need, obviously you need to go ahead with gradient descent, or maybe you play with the gradient, you add, you compute a momentum out of it, maybe you normalize it with some moving average of the variance, and that's going to be this, right? All things that we have done before, so dropout, batch normalization, you can again implement them here. The main reason that I discussed them back then was because that was easier, right, for MLP. But you can essentially do the same thing here, right? If, for instance, you are doing dropout, it means that some of the pixels in that map, you are simply dropping them, right? You just generate the same format mask, and you match it on your input when you are doing the forward pass, right? And the backward pass, those guys are not showing up in the gradient. Your gradient is going to be every time computed with respect to mask. This can hopefully help you with overfitting, right? Input normalization, batch normalization, whatever we have done with the data, right? If you want to just get out of outliers, other things on the data that you have, which now is a tensor, is totally fine. You can do it exactly as before. You just need to extend the dimension in your own mind. Any questions? Everybody's cool? Okay. That's it. One tiny note here, because those of you who are using PyTorch, you might see that this convolution that we're talking here is implemented as 2D convolution there, right? And you might ask me why this is 2D. Don't we just multiply two three-dimensional tensors together? Well, that's right, but this 2D is not referring to the objects that you are dealing with. It's referring to the kind of operation that you do. You get your filter, you put it on your input, and you just slide it left, right, up, down, right? This is the way that you do it. It means that you slide it in 2 dimensions. Why you do it? Because your filter is smaller than your input in 2 dimensions, right? Width and height, but it's matching in depth, right? Correct? Now, you could do it 1-dimensional. This is the one you have done in your assignment. You can do it 3-dimensional. How does it look like? 1-dimensional means that you have the filter which is matching the input in 2 dimensions, maybe in depth and height, right? And it's only not matching in width, right? The only way that you can scroll is in that 1 dimension, right? When you do this, this is 1-dimensional convolution, right? 1D convolution. You might have a filter which is not matching in any of the dimensions, right? Not height, not width, not depth, right? Then you can start at the first patch, which is a tiny patch in a bunch of front channels, right? And then you keep on going 2-dimensional. Once you're over, then you go 1 step in terms of depth, right? And you keep doing this, right? Now you have this mobility, this possibility to move your filter in 3 different directions, right? And this is what we call a 3D convolution, right? So it's again the same convolution. If you have a filter which is matching, that 3D and 2D are not different, right? They are essentially, I mean, same operation. only it enables you to reduce or increase the number of parameters, basically the channels you have in your filter, right? So this is the case that we always talked about. This is the most conventional one, the most favorite one, because typically the number of channels we have in our data is not significantly large as compared to the number of pixels you have. But you can also do it this form, right? So you can say that, okay, I'm going to match the height and depth, and I can only move my filter in one dimension, right? This is what you have in assignment 3. Or you could have this guy, right? You could have a small cube as the filter, right? You put it first on the first patch, you compute here, and then you keep on going also in depth, right? So you have more degrees of freedom to move. This is going to enable you that with one filter you compute a very large tensor at the output, right? But obviously this guy here is not as informative as what we have done up to this point, right? Because to compute this guy, this very maybe deep high channel output, we did not need to have multiple filters, right? We had just one filter, right? And this means that all of the features here are computed with the same bunch of weights, right? And it's too much to expect from a tiny filter to extract so much features for you, right? Whereas if you do it with multiple filters, you're going to give more parameters. This means that you are capable of learning better, right? And if you go for one-dimensional case, that is extremely good, but the issue is that you are somehow going towards the fully connected feed-forward neural network, right? You're pretty much doing the same thing as an MLP, right? MLP is essentially the convolution, 0D convolution, right? Your filter is matching in every single dimension to the input, right? And going one dimension is still too much of parameters, right? And it's somehow losing the variation or shift invariance property in your image, right? 2D is a kind of sweet point. This is what everybody is talking about it. Okay? Questions? No question? Okay, great. So that's pretty much this here. So yeah, all of the operations are the same. Now, we have talked about CNN, and that's it. But one thing left, which is the next chapter, that is ResNet. Okay? And ResNet somehow started when people got confident on this guy and tried to make it deeper and deeper. So people started to just make it deeper and deeper, and each time they saw better and better performance. But at some point they started to see that, well, at when we go deeper than something, nothing is getting improved. Actually, it's getting worse, right? And then the question was why this is happening, right? There had been a bunch of people who said, finally, backpropagation is not working, right? But yeah, people found out this is simply gradient vanishing gradient property. And they tried to get rid of it. How they did it? They just added something that we call a skip connection. Nowadays, every serious architecture that you have, almost all of them have skip connection. And the next thing we want to talk about is a skip connection and how we can interpret it as what we call a residual learning. This is going to conclude the ResNet that we have now, and also it's going to help a lot all across the semester. Questions? No question? Everybody's cool? Okay, so see you on Thursday with ResNet.